Hi. For our next lesson, you're going to need three things. Your Nuclear Fission and Fusion notes page, which you can download on a link above this, a writing utensil, and a periodic table. Today, we're going to be talking about our first nuclear reactions. So we're going to be talking about nuclear fission and nuclear fusion. So nuclear reactions are like chemical reactions. They involve changes in the matter. But in the nuclear reactions case, they involve changes to the composition of the nucleus. And so when we have a nuclear reaction, the number of protons or neutrons either changes or their arrangement changes. So we say the number, we mean we start off with 5 protons and maybe we end up with 4 protons, or we start off with 7 neutrons, we end up with 8 neutrons. We say arrangement, we mean that maybe we start off with 4 neutrons over here and 3 neutrons over here, and afterwards we end up with like a big chunk of 7 neutrons. Just their location changes and the way they're arranged with each other's change. And so nuclear reactions involve one of those two things, either a change in the number of protons or neutrons or a change in the arrangement of the protons and neutrons in the nucleus. The two major types of nuclear reaction are what we call fission and fusion. And so in nuclear fission, the nucleus splits apart. Usually we start off with a large nucleus and it splits. We can almost hear the word, there's a word fissure or the word division. So fission means to split. And so in fission, the nucleus splits. In fusion, they join. If we fuse two things together, we've taken two things and made it into one. And so in nuclear fusion, we have two nuclei, that's the plural of nucleus. So two nuclei, usually small ones, that join together to make a larger one. So fission, one big nucleus splits apart into multiple pieces, usually 2. And in nuclear fusion, two nuclei, two individual nucleuses, join together to form one. Two small guys form together to form one bigger one. So let's start with fission. We need a large nucleus to start with. And so on the periodic table, the largest naturally occurring element on Earth in terms of atomic number is uranium. And so this is uranium-235, this isotope. If we were to take a single neutron and we were to shoot it at an extremely high speed, a very large kinetic energy neutron, at that uranium-235 nucleus, that is what we would need to start a nuclear fission reaction. And this is just one example. This uranium-235 fission is just one type of nuclear fission, but it always has to start with a large atom. So we shoot the neutron at the uranium-235 nucleus. When it hits, it joins with that nucleus and it creates a new isotope. So it's gone from uranium-235 to uranium-236. Its mass has gone up by 1. And that makes sense because we just added a neutron. If you add a neutron, which has a mass, since mass is protons plus neutrons, we add another neutron to uranium-235, we'll get uranium-236. Now, while this can happen, what's called neutron capture, whenever the neutron sticks to a nucleus, in order for it to be fission, something special has to happen to the new isotope that forms. It has to be unstable in a particular way. And so uranium-236 is showing it by the spikiness. It's not really spiky, but it's showing that it's unstable. And so when it's unstable, here's what's going to happen next. Things that are unstable want to reach a more stable state. So the uranium-236 nucleus splits into two new nuclei, krypton-92 and barium-141. These two nuclei are both more stable than the uranium-236. So because the nuclei are more stable, that means the nuclear potential energy drops, the potential energy in the nucleus decreases because we got to a more stable state, and it means that that energy had to go somewhere because energy can't be created or destroyed. And where it goes is into kinetic energy. So when this nucleus splits and fissions, there's going to be kinetic energy released. How much kinetic energy? So the answer is a lot of kinetic energy. This photo right here is a photo of the same nuclear fission reaction that we just saw in the last video. This was an atomic bomb test in the 1940s. This was the Baker test. The atomic bomb was exploded underwater. This was a fission reaction of a chunk of uranium that was really relatively small. It's one that a couple people could lift up and pick up if they wanted to. And to give you an idea on scale, this is about 3.5 miles away from this. These dark objects here are battleships and aircraft carriers. This right here is the Japanese super dreadnought battleship Nagano. It's about a little over 700 feet long. And so just gives you an idea of the scale of this particular nuclear explosion. So this is an atomic bomb. What is the nuclear reactions that are used in traditional atomic bombs are nuclear fission reactions. They involve splitting uranium and fissioning uranium atoms or plutonium atoms, and that releases an enormous amount of kinetic energy. So once it releases that kinetic energy, it's gone from the unstable uranium-236 to the more stable krypton and the barium. It's released a huge amount of energy, but it's also released 3 new neutrons. Now, these neutrons, because they have so much kinetic energy, fly off at incredibly fast speeds. But if you remember, what started this reaction in the first place was a fast neutron hitting a uranium-235 atom. So if we had a large chunk of uranium-235, once one fissions, it then releases 3 neutrons to hit 3 more uranium-235 atoms, which will then fission to release 3 more each, now going to 9 neutrons, hitting 9 more, hitting 27 more, 81 more. We get a nuclear chain reaction. And so that's what happens in an atomic bomb. That's what happens in a nuclear power plant, but much more controlled, is that we start the fission of uranium-235, it becomes unstable, splits, becomes more stable into 2 new nuclei, releasing kinetic energy, and in some cases, releasing neutrons to keep the reaction going and keep that chain reaction happening. And that's one of the reasons why nuclear fission releases so much energy. One is because just this fission reaction releases a lot of energy, and 2, because it keeps the reaction going. It increases it until it just expands and expands and expands until either something stops these neutrons or the chunk of uranium or plutonium blows itself apart and no more fission can happen. So one thing I want you to notice is that in a fission reaction, the protons and neutrons rearrange, and we said that's possible in a nuclear reaction, as they go from 1 nucleus into 2 nuclei, but the total number of protons and the total number of neutrons does not change. So we start off with 1 neutron that's flying in, going to hit the uranium-235. If we look over uranium, it'll have 92 protons, and 235 minus 92 gives us the neutrons, 143. We have a total of 144 neutrons. Uranium-236, 92 protons, stays the same, and 144 neutrons, stays the same. It's just that now they've rearranged to become 1 nucleus instead of a nucleus and a lone neutron. When it splits into krypton 92 and barium 141, krypton 92 has 36 protons and 56 neutrons, and the barium 141 has 56 protons and 85 neutrons. If we add up 56 plus 36, 92, the protons didn't change. They've just been divided into 2 different nuclei. The neutrons, 56 plus 3 is 59, 59 plus 85 is 144. Total neutrons never changed in this fission reaction. Protons stay the same, neutrons stay the same, they just change where they're located. They rearrange themselves. The second type of reaction is nuclear fusion. Everything previous was fission, splitting large atoms. Fusion is when we start off with 2 small atoms, and these 2 nuclei have to hit each other at an extremely high speed. The reason why is because the protons inside the nuclei, they don't want to be near each other. And so to get them close enough to be able to bind together, to stick together and fuse, we have to have them going at an extremely fast speed to overcome their repulsion due to their positive charges. And so we have to have the original substances at a very high thermal energy in order for fusion to happen. So the most common place you see nuclear fusion is the sun. You can't see it directly because it's in the core of the sun, not on the outside of the sun, but there is nuclear fusion in the core of the sun. And the one thing we know about the sun is it's hot. So that's the reason why these hydrogen atoms have to be going incredibly fast to be able to slam into each other hard enough to overcome their repulsion and fuse together. So we first, 2 nuclei hit at an incredibly high speed. They collide at a high speed. 2, when they collide, they join together, forming a larger nucleus. Now, in this case, if the two original nuclei have very low atomic numbers, they're very small nuclei, then the new nucleus is more stable than the original two. Therefore, it has a lower nuclear energy. And if it has a lower nuclear energy, then that means there must be kinetic energy released, because if the nuclear energy drops, the kinetic energy has to rise because of the fact that energy is conserved. Well, how much energy is released? Once again, the answer is an enormous amount of energy. And in this case, this fusion reaction is far more energetic than the fission reaction we saw before. So this is what's called a thermonuclear bomb, or a hydrogen bomb. And it's called that because it fuses hydrogen together. So to give you an idea, whereas the last one that we saw, the Baker test that was in the ocean with the battleships around, was taken from about 3.5 miles away, and we could see the battleships of several hundred feet. This particular is atom bomb, or this hydrogen bomb, is the Castle Bravo test. This is taken from a distance. This picture is taken from a distance of about 85 miles away. This cloud, this fireball, is approximately 10 miles across. So this was fissioning, in this case, hydrogen and lithium, another small element, element number 3, and in it we fissioned a total of about 880 pounds of material that released in a very short time, in a matter of just a few seconds, enough energy to create a fireball that's 10 miles wide. And so we can see nuclear fusion releases also an enormous amount of energy. As that nuclear energy drops, it releases that fusion energy into kinetic energy. So the energy that's released whenever the nuclear energy drops as it gets to a more stable state is released in the form of heat. And so that makes all the other nuclei around move a whole lot faster. They have a greater kinetic energy. Well, but remember what caused these two hydrogen nuclei to fuse in the first place. They had to be going very, very fast. Well, if we heat up all the other hydrogen nuclei, we're going to make them go even faster. And if they're going even faster, then when they slam into each other, they'll fuse as well, releasing more energy, heating things up even more. And that's how fusion has a nuclear chain reaction, is that unlike fission, where it released more neutrons, which broke apart or stuck to the uranium and made it keep going, in fusion, it's about keeping things hot, is that if the fusion reaction releases enough heat that doesn't escape, it heats other atoms up enough to keep them fusing, which releases more heat, and that's why we have a chain reaction. What I want you to notice is, just like in fission, the protons and neutrons rearrange. They go from being in 2 nuclei to being mostly in 1 nucleus, but the total number does not change. We start off with 1 proton in this hydrogen nucleus, 1 proton in this hydrogen nucleus, total of 2. At the end, we end up with 2 protons in this helium nucleus that it fused together to form. The neutrons, we start off with 3 total neutrons. We end up with 3 total neutrons, so 2 in the helium and then 1 that's off by itself. Keep in mind that unlike the fission reaction, this neutron is just released. It's not involved in the chain reaction. It's the energy that's released that keeps these atoms moving super fast, that keeps new hydrogen atoms going fast enough to run into each other, to collide and to fuse, to release yet more energy. So that nuclear potential energy that we talk about, when it gets to a more stable state, the potential energy drops in the nucleus. That's the nuclear potential energy. Is sometimes called binding energy because it's what binds the nucleus together, what holds it together. It changes depending on the atomic mass. And so this graph sort of gives you an idea of atomic mass on the x-axis and the average amount of nuclear energy or binding energy, nuclear potential energy per proton and neutron. And so we can sort of see that for really small atoms, they have a pretty high nuclear energy on average per nucleon, per proton or neutron. But as they get bigger, that nuclear energy drops until we get to iron. When we get to iron, the nuclear energy slowly starts to rise again. And this explains why fission only produces energy when you use large nuclei. If I have a large nucleus like uranium and I split it in half, the nuclear energy drops. It gets more stable, and that energy is released in the form of kinetic energy. But if I were to take something small, like something like oxygen, and I were to try to fission it, try to split it, when I split it, the nuclear energy would go up. So if the potential energy goes up, that would be getting less stable, not more stable. So small atoms don't typically want to fission. Large atoms are more likely to fission, and if large atoms fission, they give off energy. If small atoms fission, they actually would have to absorb energy. You could not make a standard nuclear fission bomb out of oxygen or carbon, or even iron. You can't do it. But fusion, on the other hand, happens when you take two small atoms and you join them together. And so if we have a high nuclear energy, we join them together, the nuclear energy drops. If the nuclear energy drops, the energy has to go somewhere. It's released in the form of kinetic energy, but only if the atoms start off small. If I took something like bromine, a much larger atom with a mass of 85, and I tried to fuse two bromine atoms together, they would go from that up to here. The nuclear energy would rise, and if the nuclear energy goes up, that means the kinetic energy goes down, and so that would not release any energy. So you can't really do something where you fuse iron and get energy out of it, because by fusing iron, you'd be increasing the nuclear potential energy, which means you'd be decreasing the kinetic energy. And so to get a good nuclear reaction, you always want to be releasing energy from potential into kinetic and not vice versa. So let's get an idea on the actual amounts, like numerically. Fusion of small nuclei and fission of large nuclei, the only case to get energy out, release much larger amounts of energy than in chemical reactions. So let's suppose you had 3 million gallons of gasoline and you lit it on fire, and you look at all the thermal energy released by that. That'd be very exothermic and a lot of stuff reacting. Well, if you were to fission just 1 kilogram, about 2.2 pounds of uranium, of that uranium we looked at before, it would release pretty much the same amount of energy as burning 3 million gallons of gasoline. So very, very large amounts of energy we get by fission. The nuclear energy drops by a lot, which means it gives off a lot of kinetic energy. Fusing 1 kilogram of hydrogen would release as much energy as burning 12 million gallons of gasoline. Now, much more, so about 4 times as much energy per unit mass as fission does, but in both cases far more than we get by chemical reactions. Now, in our electricity generation, we do use fission. Nuclear power plants tend to fission uranium or plutonium to generate energy. We do not have any nuclear power plants that currently fuse things. There are experimental reactors. There's one that's being built in Europe right now called ITER, I-T-E-R, that's attempting to do this. But right now we have not figured out technologically how to keep materials hot enough to keep the fusion going. They tend to lose their energy to other forms because, as we talked about first semester, energy wants to try to reach a more stable state, and that means becoming more evenly spread out. And so we've had a lot of trouble trying to work out fusion as a power source. We can use it in thermonuclear bombs and hydrogen bombs, but we don't know how to use it as a power source yet. If we do, it will be an excellent source of energy because it will release far more energy than fission does, far more energy than burning natural gas or coal, or far more energy than things like wind or solar. It's just we don't know quite how to do it yet.